So let's revisit the double slit experiment, and we'll look at an example of a type of question we could ask. So if I've given this picture where I have a red laser through a double slit, and it's creating an interference pattern where I see a maximum, a central maximum actually, my first maximum to the side, my second maximum to that side, my first maximum to the other side, so on and so forth. I see this interference pattern show up. I could do the same thing with a different laser. I'm going to use a different laser. It has a different wavelength, a different color. So this one is 650 nanometers. This one's 520 nanometers or so. If I were to look at these and send them through exactly the same slits, does this make sense that they are that this wavelength is shorter than that wavelength? So if they go through the same slits, they go to the same screen, we should be able to know what we know about maximums and minimums and path length difference and figure out this problem. So we're going to shoot these lasers to the same two slits and see what happens. However, we know that d sine theta, this d is the distance of the slit, the separation of the two slits. Sine theta is the angle, so if I'm coming in, if I'm looking at the screen and I'm some distance away from this screen, shooting at it, this angle, I'm going to open up an angle in front of me. So I start at 0 degrees and I go maybe 2 degrees to the side. And I see that I get a maximum there. So my d sine theta is equal to m equal 1 times lambda. So I can figure out the angle between these two positions. It's proportional to, there's a triangle that we can use to figure out the distance between them, the actual measurement. But we can just think of the angle. So if I look at these two and I go d sine theta for this, my theta is large here, which means m lambda has to be specific value. If I look at d sine theta for this, the bottom one, the green color, I know that my d is the same. My lambda may be different, but I definitely know that my theta is different. This angle between these two lines, or that would cause these two lines to form at two positions, is smaller than the angle up here. So if this angle is smaller, d is the same. I'm looking at my first maximum to the side, so in both cases, the first maximum, so m is the same. So by just looking at this picture, I should be able to deduce that the red light has a larger wavelength because it has a larger angle, and the green has a shorter wavelength because it has a shorter angle. So if we were to, look at these, we can see that, again, this distance here shrunk because the angle that created it was smaller. It's a shallower angle, or it's a less of an angle. It's less off to the side than the red one. So I didn't quite say what the right wavelengths were, but the top one was produced by 670 nanometer light, so a pretty moderate visible wavelength, 670. We can see up to about 750. So 670 is very red, and we can see that the green is 520. So it does, our problem that we asked of ourselves is the wavelength for the green shorter than the red? And the answer is yes. And if we actually were able to accurately measure this distance or measure the angle between these, we could actually determine one of the wavelengths from the other one. So it's kind of a cool little problem that we can work out, and we see a lot of these types of problems. So the longer the wavelength, the longer or the larger the angle is. And there's other problems we could ask. We ask, what happens if we change the distance, the spacing between lines, between, not the lines, but the slits. If we make the slits larger, what happens to the angle or the pattern that we see? If we look from, instead of m equals 0 to m equal 2, we could look from m equals 0 to m equal 1. We could ask, what's the angle between these two compared to the angle between these two? Lots of different questions that we can ask, and this is really the heart of the interference problem. And there's some really interesting effects that can happen. But again, all the physics that is required to do this is just a little bit of geometry on top of the difference of path lengths have to be exactly an integer value of the wavelength to be constructive interference, or if we have complete destructive interference, a dark band, that means we have a half integer value of their path length, a half integer wavelength difference between the two path lengths from the two slits. So again, the smaller the wavelength, the smaller the angle that created it.